So welcome to lesson 2A. We're going to talk about primary trigonometric ratios. So again, this was introduced in grade 10. In grade 10, you would have taken it much more slowly, covering each primary trigonometric ratio in one period. Today, we're going to combine everything. So it's a review lesson, but also if you don't remember it, it's time to refresh your mind and hopefully you become more fluent with these types of questions. So we've separated into two parts. The ratios part one will specifically look at how to write the ratios as well as how to solve for angle of interest. In part two, we'll specifically look at how to solve for specific side lengths. So primary trigonometric ratios. There are three primary trigonometric ratios for any right triangle. I want to emphasize that a lot because we are going to eventually learn tools that can only be used for right angle triangles and tools that can only be used for obtuse or acute triangles. So you need to, in your head, kind of separate out these processes. Which tools can I use for which scenario? So there are three primary trigonometric ratios for any right triangle. The three are sine. Again, emphasizing the E there, it's not sin, it's sine. We also have cosine, as well as tangent. We know that within the mathematical language, sine is reduced to S-I-N. Still pronounced sine, it's not sin, but I can't just write sine like this. Whenever I have a primary trigonometric ratio, it's always attached, a primary trigonometric function, so in this case sine, it's always attached to an angle. So sine theta is more appropriate. This angle is your angle of interest. It could be any number, so it could be sine 30, sine 50, so on and so forth, but you can never just have the sine by itself. It must be attached to an angle, which is called its argument. Similarly, cosine is COS, but again, it has to appear with an angle, so cos theta or cosine theta. And here we have tangent, so TAN, again, it can only appear with an angle, tan theta or tangent theta. So to solve trigonometric ratios then, we can use the acronym SOHCAHTOA. You should remember this from last year. So SOHCAHTOA essentially tells us which trig function, so sine, cosine, or tangent, we should use depending on the scenario that we have. So the O's and the H's and the A's, those are just the special words we learned last class. Opposite is O, H for hypotenuse, and A for adjacent. So if we follow SO, S stands for sine theta, is equal to opposite divided by hypotenuse. Cos theta, so ka, is adjacent divided by hypotenuse. Sorry, I just think it's a bit unclear. I'm just going to try to focus it. Okay, it's about the same. And tangent is TOA, so opposite divided by adjacent. Okay, so that's what SOHCAHTOA means. It essentially tells you to find the trigonometric ratio for sine theta, where theta is an angle of interest. You take the length of the opposite and divide it by the length of the hypotenuse. To find the trigonometric ratio associated with cos theta, where again theta is an angle of interest, we do the side length of the adjacent divided by the side length of the hypotenuse. And to find tan theta, we do the side length of the opposite divided by the side length of the adjacent. So what we first need to be able to do is we need to be able to write out these trigonometric ratios, and then we can focus on solving different aspects of them. So steps. Writing primary trigonometric ratios. I'm going to try to keep this here so we can still see the SOHCAHTOA. The first thing you always need to do is make sure that the triangle is a right triangle. Again, I'm emphasizing that. SOHCAHTOA only works for right triangles. label the triangle using the words opposite, adjacent, and hypotenuse based on the angle of interest. So this is what we learned how to do last class. And identify the relevant trigonometric ratio using the acronym and substitute the corresponding numbers from the triangle. So here, what I want to do is I want to show you, we have identical triangles. We're going to choose different angles of interest. Here we can see it's sine A. Remember that the argument attached to the sine represents the angle, and that represents this angle here. So for the first three trig ratios, A will be our angle of interest, and for the next three, C will be our angle of interest. So let's get back to just this first example. It says use the following triangle to determine the primary trigonometric ratios. So the clue here is usually we see sine theta or cos theta or tan theta. This represents our angle of interest. Here, our angle of interest is A. So I'm just going to take a color. I'm going to take this red. I'm just going to go over this in red to remind me that this is my angle of interest. Based on my angle of interest, I should be able to name the sides with those special names: opposite, adjacent, and hypotenuse. So remember, you always start by naming the hypotenuse first. It's the side, the longest side, so 5, but also the side that's opposite to the 90-degree angle. So we can call this our hypotenuse. I'm just going to call it HYP for short. If this is our angle of interest, remember our adjacent is the side that is touching or close to that angle of interest. So that's my adjacent, and therefore this is my opposite. Okay, so we need to find the relevant trig ratios. We've labeled our sides. Now we're going to find our ratios. We know from SOHCAHTOA, or essentially this, that sine an angle, the sine of an angle, is equal to the opposite over hypotenuse. In this particular case, my opposite is 3 and my hypotenuse is 5. So again, I don't really need you to show this step ever. I do need you to go from sine A to 3 over 5, just like that. I'm just showing it here so that you're understanding where I'm getting these numbers from. Similarly, cosine A is the ka, adjacent over hypotenuse. So cosine anything would be adjacent over hypotenuse. In this case, my adjacent is 4 and my hypotenuse is 5. So cos A is 4 over 5, or 4/5. And tan A, this is TOA, so this is opposite over adjacent. And so the opposite here is 3, and the adjacent here is 4. So tan A is 3 over 4. And this is what a primary trigonometric ratio is. The sine of this particular angle, even though we don't know what that angle is yet, is always going to be the ratio of opposite to hypotenuse, which in this case was 3 to 5. The cos of A, an angle of interest, was 4 over 5, and tan of A was 3 over 4. Now we're going to do the same thing, but we're going to just change up our angle of interest here. So it says use the following triangle to determine the primary trigonometric ratios. The only thing that's changed here is we can see that instead of sine A, we have sine C. So C is our new angle of interest. Again, I'm going to just mark that in red so that I remember what my angle of interest is. So again, I can label the triangle. So I start with hypotenuse always, because that's the longest side. So hypotenuse. Now I look at my angle of interest. The side touching or close to my angle of interest is my adjacent. And the other side will be my opposite side. So what we've noticed again is the hypotenuse always stays the same. The opposite and adjacent can vary based on our angle of interest. So we're going to do the same thing. We have sine C. Sine is always so SOH, opposite over hypotenuse. In this case, my opposite is 4 and my hypotenuse is 5. Then we have cos C, which is ka, so AH, adjacent over hypotenuse. So adjacent 3, hypotenuse 5. And tan would be oa, so opposite over adjacent. In this case, opposite is 4 and adjacent is 3. Okay? So what we see is that the trig ratios can change based on the angle of interest. Here, when the angle of interest was A, the sine A was 3 over 5. But when we change it to an angle of interest of C, sine C is 4 over 5. So what this essentially tells you is that the angle of interest is very important in determining the trigonometric ratio, because the angle of interest essentially determines what the opposite and what the adjacent sides are. So that's how you find a general trigonometric ratio. What we're going to do in the next exercise is we're going to have to choose between sine, cosine, or tangent based on the scenario that we've been given. So using the information provided on the triangles, create the correct trigonometric ratio. The dot represents the angle of interest. Okay, so let's start this. This we know is our angle of interest, which I've shown again in red. We need to always start by labeling our sides. So we'll start with hypotenuse always. Here's the 90-degree angle. Opposite to that is here. So here is my hypotenuse. I know the hypotenuse is 10. Great. This is my angle of interest. So the side touching or close to the angle of interest is my adjacent side. And the other side is therefore my opposite side. What we notice here is that I've only been given 2 values. I don't know all 3 sides like I did here. I know the hypotenuse. I also know the adjacent. So using this information, you should be able to determine which trigonometric ratio you can use. So I'm just going to write out SOHCAHTOA along the top here. SOHCAHTOA. In this case, I've been given adjacent and hypotenuse, so I look around. This one has both adjacent and hypotenuse, so I know I'm trying to write a cosine trigonometric ratio. So the cos, remember, cosine can't exist alone, it needs to have an angle. In this case, our angle of interest is A. So the cosine of A is equal to adjacent over hypotenuse. So adjacent, which is 8, over hypotenuse, which is 10. Now this is great, but we have a fraction, and if you can simplify, you always want to simplify. So this is the same thing as saying cosine. I can divide both of these by 2. So 8 divided by 2 is 4, and 10 divided by 2 is 5. So the cosine of A is 4 over 5. So the 4 over 5 represents the trigonometric ratio for cosine A. Again, we don't know what that angle is, but we still know the trigonometric ratio that's associated with that angle. Okay, let's try our second example here. Once again, they've given us an angle of interest, which I'm going to show with this. Okay, and I need to label the sides. So I'll start with the hypotenuse. Here's a 90-degree angle. There's the opposite side. So here is the hypotenuse. The side closest to the angle of interest is my adjacent. And the side opposite is my opposite side line. So in this particular scenario, they've given me an opposite. I know it's 7. They've also given me an adjacent. I know it's 2. So I need to choose a trigonometric ratio that can be described using opposite and adjacent. It's not so, it's not ka. This time we're using toa. Okay, so when I'm writing this out, I have tan. Again, tangent can't exist alone. It must exist with an angle. The angle of interest here is F. So tangent of F is equal to opposite over adjacent. In this case, opposite is 7 and adjacent is 2. We can't simplify that any further, so this is your final answer. The primary trigonometric ratio associated with tan F is 7 over 2. Now, let's take a look at this, and you're like, that looks really weird because the triangle's kind of off to an angle. But the thing I want you to always remember, is that this SOHCAHTOA, the primary trigonometric ratios, only work with right triangles. As long as you see this marking that indicates that there's a 90-degree angle, this is a right triangle, you can use SOHCAHTOA. So again, I'm just going to label the angle of interest in red, and I want to label the sides. So here is my 90-degree angle. The side opposite will be my hypotenuse. Here's the angle of interest. This is the side close to the angle of interest, so that's my adjacent. And this is the side opposite of my angle of interest, so that is my opposite. In this particular question, I was given opposite and hypotenuse. I wasn't given a value for adjacent. So again, I look at my trigonometric ratios. So sine has both opposite over hypotenuse. So I know I'm going to write my trigonometric ratio using sine. So I have sine here. Again, I have to associate it with its argument and angle of interest. In this case, the angle of interest was z. So the sine of z is opposite over hypotenuse, 3 over 5. This is how we write the trigonometric ratio. So all we've done from yesterday we learned how to label the opposite, adjacent, and hypotenuse. Now we're just taking those numbers and putting them together to make the primary trigonometric ratios using SOHCAHTOA. Give me 2 seconds as I switch to the next sheet. So the next exercise, it says, using the information provided on the triangles, create 2 different trigonometric ratios. Oh, well, I should put S there, 2 different trigonometric ratios. The dot represents the angle of interest. So same deal, but now we have been given all 3 sides. We're just going to write 2 of the 3 trigonometric ratios, up to you what you want to do. So I'll do one of these examples and then I'll move on. So again, the dot represents our angle of interest, so we're going to highlight it. Based on our angle of interest, we should be able to label all our sides. So always start with the hypotenuse. It's the side opposite of the 90-degree angle. So here is my hypotenuse. The side close to my angle of interest is my adjacent. And the side opposite is my opposite. Okay, so based on this, all it says is create 2 different trigonometric ratios. It's up to you what you want to do. So for this one, I want to do cosine as well as maybe tangent. So again, cosine, I can't just write cosine on its own. It needs its argument, its angle, which is A. And let's also do tangent of A as well. So the cosine of A, again, I'm going to just write SOHCAHTOA along the top. So cosine is adjacent over hypotenuse. The adjacent here is 15 over hypotenuse 17. And tan A is opposite over adjacent. So TOA, opposite, is 8 over 15. In this case, I can't reduce either of those ratios into their simplest forms, so I keep them as is. So that's the first part of today's lesson. You should be able to look at the different side lengths and create appropriate trigonometric ratios using the angle of interest. For the second half of this lesson, we're going to focus on finding the angles of a triangle. The trigonometric ratios can be used to determine the angles of a triangle as well. Okay, so what does this mean? This means I can write out these ratios all I want, but then I can go and solve for A. So what specific angle do I need to put in as the argument to tangent to create this particular ratio? Or if we look at a previous example, what specific angle A here produces this particular trigonometric ratio? So we can then go and solve for these angles. So the trigonometric ratios can be used to determine the angles of a triangle as well. Steps. When you're solving the angles of a triangle, write the correct trigonometric ratio for your angle of interest. So that's what we've been practicing all along. And then solve for the angle using the inverse trigonometric functions. So we are going to really focus on this when we're going to focus on this when we get there. It's essentially all calculator work. So please have your calculators out, and I'm going to show you how to do it with your calculators as well. So exercise. Solve for the angle indicated with the dot. Round all angles to one decimal place. So it says solve. So that's what we want to do. So the first step is to write the correct trigonometric ratio for our angle of interest. We have loads of practice with this, and in fact, these are the same questions that we saw on the previous page. So if we take a look at the first page here, we've already solved, okay, I know my triangles are missing here, but these are the same triangles that we have. So I'm going to copy down the trigonometric ratios from our previous page. So the first one was cosine A is 4/5. The second one was tan F is 7/2. And the third one was sine Z is 3/5. Okay, so those were the ratios. Again, we've already found these ratios on the previous page, which is why I'm just copying them down. From these ratios, we need to be able to solve for the specific angles. Before we get to that, I want to show everyone things on your calculator. So on your calculator, you should see buttons for sine, cosine, as well as tangent. Above them, which you can see in yellow here, we have sine to the power of -1, cos to the power of -1, and tan to the power of -1. Now, we don't think of them as to the power of -1. That's the first misconception. When you see that notation, essentially we're looking at inverse trig ratios. So if I want to access the yellow kind of functions there, see how I have a shift button that's yellow? I will press the shift button, and when I press sine, instead of sine, it gives me the inverse sine. Similarly, if I press just cos, I get cos, but if I want to access the yellow letters there, I press shift and I press cos, it'll give me the inverse of cos. Now, different calculators might do this differently. You might have a different color. So let's say I want to access this D, which is capital D, which is in pink. I would have to press alpha and press that sine button. So look at the color that's associated with your inverse trig ratios. Find the button you need to press to access those inverse functions, and that's how you're going to access them. Okay, so that's the first thing. Another thing is, I'm just going to show you a quick example here. When the way my calculator works is I would press the inverse, then put the ratio in brackets. So let's say it's 3 divided by 5. And it'll give me an answer. For some of you, you might have to put in the ratio first and then click the shift and the sign. So you need to play around with your calculator because different calculators do work differently. So let's take a look at this question. Here I have cosine A is equal to 4/5. To solve for angle A, so remember I said that cosine, sine, and tangent can never exist without their argument. They can never exist without their angle. So we can't just move the cosine away from the angle unless you use the inverse trig ratio. So to solve for A, again, you have to write it out on your calculator. What you're going to do is you're going to do the inverse of cosine. So instead of cosine, you're going to do the inverse. So I'm going to press shift and do the inverse. And then I'm going to type out the ratio, so the 4/5 in brackets, 4 divided by 5. And that gives me 36.86989765. So I'm just going to write it all down quickly. 36.86989765. So what does this A represent? This A represents the angle. So I'm going to put a degree sign to represent the angle. Now, in our question, they said to round it to one decimal place. So A is equal to 36.9 degrees. What does this mean? Like, why did we solve for this A? That just means in order to produce this particular triangle where the adjacent side is 4 and the hypotenuse is 5, the angle of A must be around 36.9 degrees. So essentially, it's just like solving for an equation. Essentially, I solve for what value of a should I put into this equation to get 4/5. So let me try that. Let me put cosine. So I'm going to do cosine 36.869896765. So I've replaced a with the value I solved for. And that gives me 0.8, which is the same thing as 4/5. So essentially, what we're doing is we're solving for the angles that we can put back into this original equation to make the left side equal the right side. Now, I do want to show you, some of you might have learned in the past, you can rewrite it like this. To solve for angle A, essentially, I'm doing the inverse cosine function and then typing in the ratio. This is what you're doing, yes, but it is incorrect to write that on paper. So that's what I mean that you should always use calculator. You should always just do it in your calculator. So let's try this next question. It says tan f is equal to 7/2. Again, I want to isolate for the f. Normally, we can't separate the angle from the trig function, so tangent has to be associated with the f. The only way you can separate it is if you use an inverse function. So we're dealing with tan this time, so the inverse function is this. Essentially got it by pressing shift and tan. And then I put my ratio in brackets. So the ratio is 7/2, 7 divided by 2, which gives me 74.0546041 degrees. Again, I'm going to write it all out. So 74.0546041. Again, degrees because we're solving for an angle. And based on the instructions, I should isolate, I should round it to 1 decimal place. Something I should have done is I'm going to actually go back. I'm going to put a little dot above here. Remember, the dot above the equal sign means it's approximately 74.1 degrees. Again, what does that mean? That means this angle must be around 74.1 degrees in order to produce a triangle with a ratio of 7/2 as its opposite and adjacent. So again, I'm going to do that same thing I did previously. If I take this value and plug it in here, so if I do tan 74.0546041, I get 3.5, which is 7/2. So I'm just trying to figure out what angle can I put into these expressions to make left side equal the right side. The last ratio we have is sine z is equal to 3/5. Again, I'm isolating for z. In order to do that, I need the inverse trig ratio. So I was dealing with sine, but its inverse would be shift sine. And then again in brackets, I'm going to write out the ratio 3/5, which gives me 36.869896765 degrees. So that's about 36.9 degrees. Again, only if this angle is 36.9 degrees can I make this particular trig ratio. So hopefully that's clear on how you can solve for these angles. What I do want to suggest is if you have a calculator that isn't working properly, maybe during our next live lesson, you can come show me what your calculator is doing so that I can show you how you should press your buttons to get these trig, to solve for the particular angle. So the last exercise that I want to kind of look at is this. So create 3 different trigonometric ratios for this triangle. The dot represents the angle of interest. Then solve for the angle using all 3 trig ratios and see what you get. Okay, so let's highlight our angle of interest here. That's our angle of interest. Based on this, we can start naming our sides. So the side opposite to the 90-degree angle, that's always my hypotenuse. The side closest to the angle of interest, that's my adjacent. And the side opposite of the angle of interest, that's my opposite. So I have these three sides. They want me to make all three trig ratios. So sine, remember, sine has to be associated with an argument, an angle, which is A. The sine of A is equal to SOHCAHTOA, so opposite over hypotenuse. Let me just write it over here again. SOHCAHTOA. So opposite over hypotenuse, 8 over 17. The cosine of A is equal to, so cosine is adjacent over hypotenuse, 15 adjacent over 17 hypotenuse. And then we have tangent of A. Tangent is OA, opposite over adjacent is 8 over 15. So I've created three different trig ratios. I want to now solve for the angle using the three trig ratios. So using the method I showed you above for solving angles. So to solve for A, again, I'm going to show you this on my calculator. I'm not going to write out the full angle this time. I'm just going to round it to one decimal place right off the top. So here I have A. To isolate for the angle, I need to use the inverse trig ratio. So, the inverse trig function. So I'm going to use alpha sine to get me to sine the inverse of sine, which is indicated with that -1. And then I'm going to type out the ratio, 8 over 17, in brackets. So this tells me that A is about 28.01 rounds to 1 degrees. Let me do the same thing with cosine A, 15 over 17. Because I'm dealing with cosine, the inverse cosine will be obtained by pressing shift and cosine. And then I'm going to type out the trig ratio in brackets. So that also gives me 28.1 degrees. And if I do the tan ratio, again, to isolate for the angle, I'm going to use the inverse trig ratio. So for tan, I'm going to do shift and tan to get tan, and that's -1, which indicates inverse. And then I'm going to type out the ratio 8 over 15 in brackets, and that also gives me 28.1 degrees. So what do you notice about the angles that you solved? Well, you should notice that they are all equal. Does that make sense? And the answer is yes, because all of these trigonometric ratios were written in terms of your angle of interest A. The angle of interest A was the same here and here and here. It represented this particular angle, so all of the angles that you solved for were also the same. If you did C, so if this was your angle of interest and you did sine C and cos C and tan C and solve for those angles, again, it would be the same because you're referring to the same angle when creating these different trig ratios. So in conclusion then, you can use any of the three primary trig ratios to solve for any angle of interest. If you want to solve for A, you don't need to do sine A, cosine A, and tangent A. You can do any one of these trig ratios and it'll get you the right angle. Similarly, if you want to solve for C, you can either do sine C or cosine C or tangent C. When you solve for the angle, it will always be the same. So the homework is do handout B and then hand it in our Google Classroom. Thank you.